I'm going to provide the coordinate definitions of the sine, cosine, and tangent functions. You may know the right triangle-based definitions of the sine, cosine, and tangent functions and wonder why do we need an alternative definition. Well, the problem with the right triangle-based definitions is that they don't work for anything except acute angles. All right? Suppose you wanted to find the sine value of an obtuse angle. How would you draw a right triangle that contained an obtuse angle? Suppose you wanted to find the cosine of minus 5 degrees. How would you draw a right triangle that had an angle measure of minus 5 degrees? All right, so see the problem? With the right triangle-based definitions, the domains of the functions are limited to acute angles. All right, I'm going to give alternative definitions that are equivalent to the right triangle-based definitions for acute angles. But they're also going to work for angles that are not acute. So let me show you the definitions. All right? So draw coordinate axes and draw a circle centered at the origin. It doesn't matter what the radius is. So I will call my radius r. So the radius is some length r. Okay, now every point on the circle has a corresponding radius. Okay, so this blue dot on the circle, this blue point on the circle I've drawn has the radius that corresponding radius that I've drawn. And then furthermore, every point on the circle's corresponding radius defines a corresponding angle with respect to the positive half of the x-axis. All right, so for the blue dot that I've drawn, it defines this angle theta. Okay, furthermore, the blue dot has coordinates. Let's call them x and y. Okay, now here's the coordinate definition of the sine, cosine, and tangent functions. The cosine of theta, as drawn in the picture, is equal to x over r. The sine of theta, for theta as drawn in the picture, is equal to y over r. The tangent of theta, for theta as drawn in the picture, is equal to y over x. Okay? Let me show you now why these definitions are equivalent to the right triangle-based definitions. Okay, so we can draw a right triangle with the given radius as the hypotenuse with legs parallel to the x and y axes. So let me go ahead and do that now. Okay, in green. Now, if the coordinates of the blue point are x and y, I hope you would agree that the vertical leg has a length y and the horizontal leg has a length x, right? So using the old definition of cosine, adjacent over hypotenuse, wouldn't I get x over r? Exactly the same thing I have written here. For the sine ratio, wouldn't I get the opposite over hypotenuse? So wouldn't I get the hypotenuse leg, the opposite leg length over the hypotenuse length? So wouldn't I get y over r exactly as I have written already? And then for the tangent, the opposite leg length over the adjacent leg length, wouldn't I get y over x? Okay, so you see that the coordinate definitions agree with the right triangle-based definitions. Okay? However, these coordinate definitions are the only game in town if you have an obtuse angle or a negative angle. All right, for example, let's say we wanted to find the sine of angle alpha. Okay, so let me draw, let's say we had this obtuse angle alpha. Maybe alpha is 120 degrees. I don't know. Okay, and let's say that the coordinates of the corresponding point on the circle, I'll color it in purple, let's say they were A, comma, B. All right, so, and the radius, the new radius still has the same length. So the cosine of alpha would be A over R, because A is the x-coordinate. The sine of alpha would be B over R, because B is the y-coordinate. And the tangent of alpha would be B over A. All right? So whether you have obtuse angles, negative angles, you can find a point on the circle, and you can now find the sine, cosine, and tangent values.